Come on. All right, welcome to operating systems. Let's see if I need more volume. All right. Oh, that works well. Come on. All right, so welcome back. So this is operating systems. It is really hot in this room and it's kind of disgusting. So yeah, great. All right, off to a great start. So let's just dive into it and ask why we're even here. So why do you have to take this course? Why is it a useful course? Well, at the very core of it, understanding operating systems will make you a better programmer because you will actually understand what is going on with your computer and how to use it more effectively. So there's only two types of software you'll be writing if you're writing software, which is probably all of you at some point in your life. No matter if it's JavaScript, no matter if it's Python, no matter if it's whatever. You either write software that interacts with the operating system or it is the operating system. Those are your only two choices in life. That's it. So knowing this course, if you're using anything that uses the operating system, that's pretty much everything. Otherwise, you're going to be writing an operating system, and then taking an operating systems course is probably a good idea if you want to write an operating system. So I'm John Aelfson, your instructor. I will save you the pain of trying to pronounce and spell my last name, and I will give you some simple tricks. So that, in red, exit out, terrible, looks awful, kind of a mess. Elf, that's simple, right? Christmas is going to come up by the end of the semester, and we'll be able to enjoy Christmas at the end, so hey, elves will be in season there. That's easy to spell, I hope, only 3 letters. The next one is sin, elf sin. Perfectly valid pronunciation of my last name. Go with that, makes it easy. So if you mash them together, you get Elfson, and then if you need to spell my last name, stick a yo after the E. That's it. And then, hey, you spelled my last name with just remembering 3 simple little things that aren't that disaster of spelling. So that's an easy way to remember it in case you actually have to use it for whatever reason. Why would you need it? Well, all of the public course material will be on my website, so it's elfson.com, but spelled properly because elfson.com costs too much money, and hey, it's my last name anyways, and there's not that many of me. So all the course lecture PDFs, the links to the lab website, links to the YouTube, everything will be public, so you don't have to log into anything if you just want to look at some course material for some reason on the bus or whatever. So easily accessible, don't have to log in. And anything private will be on Quarkus. So right now Quarkus is a bunch of links. Eventually you're only going to have your grades on there, and that's pretty much it. So how the course will be structured. You will do the labs on GitLab. If you used GitHub before, then it's quite similar to that. If you haven't used GitHub before, you will eventually in your career. So GitLab is a good introduction to that. And that's how all your labs will be done. There'll be no zipping files and dropping them here or whatever. You just submit your code to the server. That's it. You don't have to do anything special. You don't have to write submit. You don't have to do anything. You just do normal software engineering things, which if you don't know, you will learn. And that's it. No fuss, no muss, no weird other additional systems. You might see that people are also using the Discord chat. So there's no Piazza, no nothing. I found Discord a lot better and less annoying, and it's a lot more interactive. So use the Discord. There's a class Discord. Last semester when I tried it, 100% of the students signed up for it. So all of you should sign up for it. Like 41% of you have already done this before I started last lecture. So it's probably hopefully even higher now. So that's great. And then the lectures will be streamed on YouTube and the recordings will be there, so don't have to worry about missing anything. So if you want to sign into the Discord, it's elfson.com/discord, and it's also, the link to that's on the Quarkus. And through doing that, it'll ask your UTR ID, whatever, that's hooked up to the central auth system, And if you use that link, it will also set up your GitLab account for free, so you don't have to do that, and also join you to the Discord server and all that fun stuff. So that's great, and as you can see in the lectures, there's a space for that for chat. So if you want to ask some questions there, you can. If I miss it and don't see it, then you can just, hey, flag me down in class and tell me that, hey, there's a question there that I need to answer, but I'll try and monitor it as best I can. With that said, lecture attendance is still important, since it is much, much faster for me to get feedback for you and sometimes for you to provide feedback to me, because sometimes you can do it passively. If I look around and see a bunch of what the WTF faces, then I know that I probably screwed up, and I'll probably screw up in this lecture because the first one had some problems. So, hey, you can ask me questions if anything is unclear, and hopefully we can resolve it in the lecture. It's just much faster. We'll also have some live coding, and we'll be able to create some happy accidents, and I'll hopefully be able to explain some of the things you tell me to do, because that's always fun, especially if you tell me to do something that's outright insane. Tell me to do it, I'll do it. We'll see if we can break my system. If you can break my system, you get something. I guess I probably can't give you grades, but hey, I'll give you something. And if there's anything I can do to make attending lectures better, let me know. First would be a call to them to turn on the AC, because this room is awful. So let's hope that is a call. So let's get the boring stuff out of the way and the evaluation for this course. So we have 12 weeks for the course. You will have 6 labs, and they'll be due every 2 weeks. And you might be looking at the list that's on the slides right now and say, hey, John, what the hell? There's lab 0, that's clearly 7 labs, not 6. Why are you trying to sneak in a lab? Well, I split lab 1 into 2 parts because most of it is set up and getting familiar with the system. So lab 0 is all set up that you don't need any prior knowledge for, and that's it. So it's just to get you set up, and then at the end of it, you do a 1-line source code change, prove you can use the server. That's it for code changes, 1 line, and spoiler alert, it's not a complicated line, it is your name. And then you answer 5 questions on CrowdMark, and then, which are mostly just feedback things, and then that's it. And unlike in other operating system courses where I found it was always kind of weird at the end of the course, you've never installed an operating system or know how to do that or have practice doing that. Well, Lab 0, guess what? You are installing your own operating system to a virtual machine, and it will be yours to break or use or whatever happens to happen with it. But you will install an operating system from scratch, so later on in your career, you'll be using virtual machines, whether you like it or not. That's just how things are. And hey, if some family member bricks their computer and can't afford Windows, hey, you can at least install Linux for them, so that'll be a great skill to have. Let's see, what else? All right, so yeah, there'll also be a midterm exam. The way this is placed is it is after reading week, because we get a fall reading week. So it's after reading week, because that makes sense. And don't worry, that reading week does not eat into your lab time. So calendar-wise, you'll have 3 weeks for one of the labs. But again, they're supposed to be every 2 weeks, so you can use reading week to study for the exam. That's kind of the idea for it. Or, you know, not be engineers and try and have a life on reading week. That would be good. So hopefully one of those is. And then we'll have a final. Lots of fun. All right, academic honesty. So you can study together, discuss concepts in Discord, post unrelated code to labs in Discord, or at least general code is fine. Most of this course is a lot of reading code, being able to explain what the hell it's doing, because some of it will be very surprising to you. Yeah, as long as it's not directly your lab code, go ahead, post it, that's okay. Do not post your lab code. Do not post your lab code on GitHub, blah, blah, blah. Don't do any of that. Technically, against academic honesty, you get in a lot of crap for it. I have to do a lot of paperwork. It's the whole thing. You don't want to do that, trust me. Your employers also don't want to see your course code on GitHub. They want to see you doing projects, and trust me, at the end of this course, You have lots of projects you can do. You can take something you want to do and just apply the concepts of this course and make it better. Lots of fun things you can do with this course. And again, cheating not going to be tolerated. It's only going to hurt you because even if you write some code, it doesn't matter. Most of this course is reading code and being able to explain what the hell is going on. So just writing code is not that big of a deal. If you just kind of pound it together and it kind of works and you can't explain it, well, that's not going to help you for exams and not going to help you for anything else, right? You don't want to be the person that needs to read Stack Overflow over and over again. You want to be the person that provides the explanation for Stack Overflow, right? So the recommended books just complement the lectures. You don't need them, but if you need an additional resource, you can have them. So it's Operating System 3 Easy Pieces. It's free. You can download the PDFs. I think it also has a web version. So you can go ahead and use that just to complement the lectures. This course doesn't follow that exactly, but it follows more or less along the same lines and just kind of ignores some of the more boring stuff and tries to explain some of the things in more detail. This course will be in C, so if you don't know C, you should know C. You should definitely know C. We will say what you should know. Hey, here we go. Here's skills you should practice again if you need. Number 1, C programming and debugging. Again, all kernels are pretty much written in C. All low-level software is pretty much written in C. Eventually, something is going to pass through C at one point or another. Guess what? JavaScript will use C pretty much directly. I think it uses C++ in some implementations, but at some point you're going to end up with C. It's actually a fairly small language. After you get over the hell that is pointers, it's actually pretty small and fairly concise. And yeah, you should know debugging. Some GDB would be okay. Printf debugging, you might run into some errors with that, but we'll kind of explain what printf actually does in this course, so you'll be able to, use it more effectively. Being able to convert between hex, binary, and decimal is a good skill to have because some of the things we'll be doing in this course have some low-level details, especially when we get into some memory things. You will definitely find that as an asset if you can just quickly convert between them or at least have some references. So when we get to that part, I'll show you some tricks to kind of remember some good reference points, and then you can kind of figure it out from there. Little endian and big endian, so hopefully you know what those terms mean from your computer organization class. And most importantly, when we get into how memory actually works, it will be difficult. So understanding how you think memory works is good, even though we will completely destroy all the notions you have of that. Just know that memory, more or less, is byte addressable. Like every memory address corresponds to 1 byte, and a memory address is basically, we can use it as a pointer, and that's pretty much it. And then past that, we will make it much more complicated. So again, please provide any feedback. This course is challenging. I've tried to rework it a bit that we spend more time on the challenging parts and get some more practice with it, and you actually get to play with some things that are more closer to what's really going on. It's not really feasible to have you create your own operating system in just a semester, but hopefully you'll get enough of a flavor of it, and we'll be reading parts of one where you'll actually get a pretty good idea where you could do it if you wanted to. So during these things, you can ask questions, right? Remember that all programs, again, even if they're written in Python, JavaScript, whatever, they're going to interact with the OS. We're going to find ways to figuring out how they interact with the OS and being able to explain that. So we can ask anything about any applications you've pretty much ever written, and hopefully by the end of this course you'll be able to explain it. Because I can guarantee you, most of you, if you tried to explain Hello World in terms of operating systems, some of you probably actually, it's expected that none of you actually know how to do it, and none of you actually knows how Hello World works. So we'll dispel that in the next lecture. But at the core of it, this is the main job of an operating system is to manage resources, and that's about it. At the core of it, an operating system should stay out of the way, and you should not know it's there as much as possible. So, a bunch of you that have used Windows before have probably sworn at Windows because you realize Windows is doing something when your application doesn't work anymore. Ideally, you never want to see Windows. You want to just use the internet, play a game, watch a video, do whatever. You don't want Windows to actually do anything except not screw up. And that's pretty much it. Just stay out of your way. So all your applications are just going to request resources. So that's what you wrote in APS 105. All you did was write like C programs, and they were applications. They ran on top of an operating system. It could have been Windows, Mac OS, Linux, whatever. It ran on top of some operating system, and it used that. It requests resources. So even if you try and run a program, that's requesting resources. You're requesting time on a CPU to run. So no matter what, your program, if you're running it, is going to request some type of resources. Other resources it might request, memory, that's a thing. Might request some disk space, access to files, things like that. But all of that, at the end of the day, is going to be managed by the operating system. So the operating system is going to manage the resources, and the operating system is what talks to hardware. So in 243, your computer organization class, you learn some things about how the hardware actually works. Well, we'll see the other part of that that's in between the application and the hardware, where the real magic happens. So you know some details, so we're going to not discuss some low-level details about how some specific hardware works. We're going to be generally how pretty much every operating system works. So there is 3 core operating system concepts. So the first is virtualization, and the idea behind that is you only have one of a particular resource, but you're going to share it between multiple things by mimicking it and trying to create an illusion that each of those things has its own complete independent version of it. So for instance, you are creating a virtual machine and installing an operating system. And it is called a virtual machine because you're installing an operating system directly on it. That operating system thinks it has complete control of that machine, even though physically I have one laptop right here and I only have one physical machine, but I'm going to have 2 operating systems running on it. I'll have Mac OS running on it, and for the purpose of this course, I'll also have Linux running on it. So it's virtualizing my machine. It's creating 2 independent copies of it that each operating system thinks it has full control over, but realistically, we'll get into some caveats where one has a bit more control than the other, but for the most part, they both have complete control over their own virtual machine. The next one is concurrency. So your days of having a single program that starts execution at main and starts executing and follows if branches and stuff, well, that is over. Your life is going to get infinitely more complicated. Don't worry, I see some worried faces already. I'll be here to help you through it, but it will it'll start off kind of like a disaster, but we'll get through it. So a way to think of this is like, hey, if I gave you a deck of cards and told you to sort it, that would be pretty easy, right? You could probably sort a deck of cards. But if I told you, hey, you have 52 people now, I'll give each of them a single card, and I want you to sort, all 52 of you, sort that deck of cards 52 times faster than that one single person. 1, that's probably not going to work, and 2, if one of you tried to explain how you would do that without killing each other, you would probably spend a while trying to explain that. One solution could just be, hey, pick the person at the front, throw all the cards at them, and then make them sort it, and then, hey, that's probably that's probably slower than one person, so that's probably not a good solution, but you kind of get the idea why it would probably be hard. The next is persistence, which is going to be pretty much at the very end of the course. Once you survive the first 2/3 of the course, persistence will not be a big deal, and you won't care that much. But the first part of the course, virtualization, concurrency, we'll get through it. It will be difficult, but you will actually know how things work, which will be hopefully good. All right, so here's a quote I was introduced to in my 4th year. So I'm introducing it to you in your 3rd year because this is insanely true. All problems in computer science can be solved with another level of indirection. So instead of solving the problem, you make a simpler problem to solve, and then you solve that problem, and then you map one to the other, and you're all good. So we're going to think about how programs even execute now. So our first abstraction in this course is called a process. So whenever you wrote hello world or anything like that, whenever you compiled that program, you got an executable at the end of that, right? Well, that executable we're going to call a program, and that executable is actually nothing that special. We're going to rip it apart and see how truly not special it is. But it's just a file, and all that file contains is a bunch of it telling the operating system what to do, and then aside from that, there's your instructions, which is basically like your assembly instructions from computer organization, and any data that's required to run, and that's it. And then what a process is when you actually run that program. So when I try to run that program, it creates a process. That process executes that program. So why did I say, hey, what's the difference between a process and a program? Well, a process is an execution of that program. It's at a certain point, and we can run multiple processes at the same time. In fact, that's like one of your main goals as an operating system, is to run a whole bunch of different processes. Most of you probably have more than one thing running on your computer. Like, you probably have a web browser open that probably has lots of tabs. You probably have, Discord on. You probably have whatever else. You have lots of things running, and they're all running as a process, and your operating system gets to manage all of those. So the basic requirements from it. So we already know that, hey, virtualization is a thing, and if we're executing a program, well, we know physically on our CPU, there's only one set of registers. And if multiple processes can run at the same time, well, if they could all overwrite each other's registers, you would probably be nothing would ever work. No program would ever work. It would, as soon as it tried to switch to another one that monkeyed with the registers, it would never work. So the first thing that would be in a process would probably be something like virtual registers. And all that means is each process would have its own independent set of registers so that one process can't interfere with another. So if two processes have different sets of virtual registers, they're independent. So other things a process would have because it is running, well, it would have a stack and it would have a heap, right, which are both located in memory. Okay, so here's my first question to you. Knowing that's a thing, how would I be able to run two different programs at the same time in terms of memory? Like, how should the operating system manage physical memory if I have two different processes, each using memory? So for example, say I'm running hello world in one process, and then in another process, it's some program that just counts up 1 every second. So if I run both of these at the same time, they're both going to be processes. Hopefully they have virtual registers, so they won't interfere with each other, but they'll be using physical memory too. So how would you think, they interact with your operating system in terms of memory? Like, anyone with any guess? Yep.
Would you allocate them memory in different positions?
Yeah, so that seems reasonable. So if my operating system is managing physical memory, well, the Hello World program, I'll just give some memory, and then if I'm the operating system and I control all of physical memory, it's not really a reach to think that, hey, it probably knows what else is free, so the next process that comes in, I'll allocate it some space for its stack, and they'll be in different regions of memory, and they'll be, they won't interfere with each other. So that seems reasonable. Anyone argue with that? Okay, reasonable, great. So the stacks for each process, they need to be in physical memory. The operating system keeps track of physical memory, just gives them different physical addresses. Still, no one thinking of any issues? Oh, yep.
I guess one curious is that if they kind of bump into each other and overlap in terms of memory usage.
Okay, yeah, first problem is, well, if they're in physical memory and if it's one then the other could use more space than it got allocated and then start screwing with the other person's stack. That would probably not be good. Yep. If you run out of memory, that could also not be good. Yeah.
Another one is that they might require different amounts of memory. So like, for example, that hello world program would need very low memory, whereas something else, like maybe a bigger game, would need a lot more.
Yeah, so one argument is they might use different amounts of memory. Specifically for the stack, funnily enough, each process gets the same amount of stack space no matter what it is. Pretty much, I think the default number now is every process gets 2 megabytes of memory for the stack. And if you use more than that, that's that stack overflow message. So yeah, running into each other's stack might be a problem, but if we believe the operating system is all magical, it may be able to monitor some process's stack, and then if it tries to run into another process, it could say no, and then you overran your stack and just get rid of it. All right, so far it kind of works. Any other issues we can think of? Okay, well, what about something you might not have thought about? Global variables. So, most of you probably don't know how global variables work. Well, how they work is when your compiler creates that program, well, that program is just sitting there, and any memory it accesses, the compiler has to know about and give an address. So if you have a global variable, the compiler just needs to pick an address for it for each variable whenever you compile it, right? So say you have a global variable x, the compiler might decide that, hey, that should be at address 1000. So anytime I access the global variable x, it actually corresponds to address 1000, and that's it. So that might be okay if we had like some global registry of addresses, maybe. So we could say, hey, Chrome, you're allowed to use address 4000 and up. Firefox, you're allowed to use address 6000 to 7000, something like that. But would there be any real bad issues with that? Yeah. Yeah, well, one big problem is that's just kind of a contract. If you just make your own program and say, hey, I'll just access, address 5000 or whatever, then you could access each other's memory. That wouldn't be good. Another thing would be that, hey, because you have to set aside certain addresses for each process, and they have to be independent and known ahead of time, well, that space is still used even if that process isn't running. So if you said, hey, Chrome, you get address 7000 or whatever I said, 4000. If Chrome isn't running, no other process could use that address because you don't know if later they might start Chrome and then there'd be a conflict and you'd be fighting over the same memory address, and it wouldn't be great. So here's what it would probably look like. We could say, hey, we could have room for 2 processes to just use whatever memory they want for global addresses, and we'll just make sure that 2 of them aren't running at the same time, maybe. That's probably a bad solution, but hey, it's a solution. And then, here's where the size is. So programs have the same amount of space for the stack, but they could have any number of global variables they want or use any memory at runtime they want. So that's where the whole memory usage discrepancy is going to come into play. Like, Hello World is not going to use the same amount of memory as Chrome running, 165 tabs open, where it uses gigabytes and gigabytes of memory. So that's not going to work. Whole lot of issues. Anyone think what might be a good solution to this memory problem? If sharing physical memory is a pain in the butt, what did we learn so far? Yeah. Virtual memory. We'll just virtualize it. So whatever we're trying to share, we'll just stick the word virtual in front of it and make sure that means that each process, if it has virtual memory, even if we're not quite sure what that entails, if each process has virtual memory, we should, even knowing that one sentence thing, know that each process would have its own independent view of memory. And then suddenly, all these problems go away. So if each process has its own independent view of memory, and it can't monkey around with each other's memory addresses and all of that fun stuff, all the issues kind of disappear. Oops. And there's also a more fun problem that comes up. So having multiple processes that are different is way easier than having multiple processes of the same program. So here's a simple little program. All it does is, let's switch to this. Whoops. All right, so here's our simple little program. Hopefully everyone can read that. Can you read in the back okay? Yeah, okay. So here's our simple program. It creates a global integer called global, initialize it to 0, and then in main, it will create a local variable called local. We are so clever with names, and that's it. So the global variable is a global variable. The local variable is allocated on the stack, and then in the program, we have a while loop. So while 1 just means this loops forever. So all we do is increment local, increment global, and then we're just going to print out its value. And then the sleep function just puts this process, since we can now say the word process, puts this process to sleep where it doesn't execute or do anything for 1 second. And then later the operating system can go ahead and execute it again. So now if we run this, well, here it's running, counting up, and then I can switch over to a different terminal, and I'm running 2 of them at the same time. So now this one is counting up, it's at what, 5, 6, 7, and this one's already at 16. So there's 2 processes, they're both running the same program, but clearly they're independent of each other because they have different values and they're not monkeying with each other. If they didn't use virtual memory and there was just physical memory, that global variable would have to be shared. And if one changed it, the other would change it. So if this said 41, then this one would also say 41 instead of like 35 when I switch to it. All right, any fun questions with that or anything you want me to do for this? So there's some experiments you could do, yeah.
Does each process just pretend it's the only thing running and allocates it somehow as virtual?
Yeah, so both of these processes, as far as each process is concerned, it has access to all the memory and it has its own CPU it's running on. So the operating system maintains that illusion, but to that process, right, whenever you wrote Hello World, you thought there was one CPU, you thought you used all of memory, that was it. So you might not have thought of it before of running 2 of the same program at the same time, but we can kind of explain that there's some magic happening here. It's sharing the CPU by probably switching back and forth between them and doing something to maintain some virtual registers. And they're also not interfering with each other in terms of memory, so there's probably something like virtual memory. We can do this experiment, but it's not going to work as well as I thought. So we can actually see their addresses. So if we want to be sadistic, instead of printing out their values, we can print out their addresses in C. Although this isn't quite going to do what I intended it to do, but let's go ahead and try it anyways. So that's just a warning that we don't have to care about. So if I run here, I get 2 addresses, and I will switch over quickly, run here, and get 2 addresses. So I'll just stop them. I can see that the local variable is at this random looking address, and let's see if they're the same between them. So this is 696C, and if I switch over to here, kill it, and go up, it's clearly different. It is 03FC, so they could be different, actually different physical addresses. We're not quite sure by looking at this whether they're virtual or physical, so that's probably kind of a lame test. And then this global variable is 0044, and if we look here, we get 0044. They look kind of the same. They're not really the same. So this one, after 0044, there is a CA, and for this one, it's a DB, but they look suspiciously more similar. So, and spoiler alert, if I turned off some setting, I forgot to do at the beginning of the first lecture, when I printed off the address of the global variables between the 2 processes running at the same time, if I changed the setting and I remembered to do that, they would have actually been the same address, which usually breaks people's brains because there's 2 things running at the same time. But hey, we know that there is some type of virtualization going on here. So any questions about that? Don't worry if it gets slightly confusing, because we're going to explain all of this by the time the course is done, and you will all be experts. Okay. So what did we find? Well, we found that the address of the local was not the same between the 2 processes, and we found that the address of global was kind of similar, but not the same between the 2 processes. So yeah, it definitely needs virtual memory, but this doesn't really illustrate it, again, because I forgot to turn off some setting. But ideally, the global addresses would have been the same between the 2 processes, and they would have still behaved completely independently, and nothing would have gone wrong between them. So this is where we can add virtual memory to our picture of a process, and suddenly everything we know about it is now virtual. So a process would have its virtual registers so that it can execute independently of another process without getting interfered with. And 2, it would need some virtual memory so that no other process, again, can interfere with it. It can pick its own memory addresses. It thinks it has complete control over memory, and that makes it a lot simpler to compile. If you happen to write a compiler, in 4th year, you're going to love virtual memory, because finding addresses is just you picking a number out of a hat and saying, this looks good to me, I'll use that, and I'll let the operating system figure it out. Unfortunately for you, that I'll let the operating system figure it out is this course. So you will be the one that figures it out. So the stack and the heap are both in memory. They'd both be in virtual memory. Again, I'll harp on this again, that each process would have its own independent view of memory so that you can't monkey with another process. And I'll also show some example code from this class. So all of the code will be in the materials repository located there. It's a clickable link if you download the PDF. If you have signed into GitLab, and I've created a repository for you, which will give you an email, then you have access to this. If not, I will have to give you access to it whenever you sign into the Discord. So this is the instruction if you want to compile the code. So you go into the directory for the lecture of the code you want to see. You type meson setup build, and it will create a build directory for you, which sets up all the compilers and does all that stuff for you. So you might have used make or something like that before. This is a more readable version of make that is not a complete pain in the butt to write if you ever have to write your own build files. This is a lot simpler. And then to compile, you just do meson compile -C, and then give it the build directory, and it will run the compiler for you and link everything together if it's more complicated than that and do all that fun stuff. And then there'll be a bunch of executables in a build directory. So here for the first lecture, there's like a count example and then read 4 bytes. And at the end, you'll get a executable called read 4 bytes. So let's dispel some magic and kind of look at this. So this is okay if this code is a bit scary right now. I will run through it and see how much of it you're familiar with. I expect you're not going to be familiar with a bunch of it. So thankfully, it starts off with main. If you don't know that it starts off with main, you are in deep trouble. Yikes. That's the part you should know. And then past that, we're going to see the arguments passed in. It checks the length of the arguments. That's what argc is. It's looking for exactly 2 arguments. If there's not exactly 2 arguments, it's going to just exit. So everyone familiar with that up to this point? Hopefully that doesn't look... Yeah, so at main, we're dealing with these 2 arguments here. This integer is the number of arguments, and this is just an array of strings. And argc says how many strings are in this array. I see a very confused...
Array of, those are character pointers.
So it's an array of character pointers. Yeah. So character pointers and strings, if you're in the C world, they mean the same thing. So I'll use the words string and character pointer fairly interchangeably. So this is an array of C strings. I'll call them C strings then. So this is an array of C strings, and this is how many elements are in the array. So I checked for 2. Always, which we will learn is just kind of a convention. The first argument is the name of the program, like the 0th argument. It's supposed to always exist. That is not necessarily true because that was the result of that not necessarily being true was caused a very large security vulnerability, which we'll see at the end of the course, but hey, fun fact. And then here, we're expecting the argument to just be a C string that is a file name. And all this code will do is open a file and then read the first 4 bytes from that file. I expect none of you have used open before, but put up your hand if you used fopen before. We got a few. Okay, we have a few. How many of you have written programs that interacted with files at all? Okay, of you that have not used fopen, what did you use? Yeah. C++, so F streams and stuff like that? Okay, so under the hood, so as long as you're running on macOS or Linux, it's actually doing this, whether it's C++, C, JavaScript, whatever. If you're interacting with files, this is what eventually it will boil down to. So if you used fopen, it kind of looks the same to this. You give it, you give it a file name and you get a file pointer back. But that is just an abstraction from the C library because the standard C library needs to work for Windows, Mac, Linux, everything. It's meant to work for everything, and to do that, it abstracted a file to a file pointer, and then it changes the actual implementation of the file pointer, what it points to, based off whatever operating system you're using. So specifically for this course, we'll be explaining things in terms of Linux, but Mac is, most things apply to a Mac as well. And Windows is a whole another can of worms, which is awful. So eventually, once you get into software development, you will hate Windows. It took me until my 4th year again to hate Windows and stop developing for it because it's a mess and you can't explain anything. But hey, we're going to use Linux. So open will open a file. It just gives a file name, and then this weird number, this magic number, just says, I want to open the file to read from the file. That's all it gets. And if you used fopen, it would return a file pointer, which is supposed to be a handle to that file. On Linux or Unixes, you don't get a pointer, you get a number back. So you get something called a file descriptor, which we'll explain in the next lecture a bit more. But basically, you just get a number that represents that open file. And at the end of this course, you'll be able to exactly know what that number should be. But for now, just a number. We're going to have some function that checks if that number is valid. So you don't have to worry about this. Most of it will be like reading API documentation to see what valid return values are. But for this, I just have a helper function to check for errors. And then here, so we create an array of characters of size 4. You should know all about arrays. If you don't know about arrays, you will have a very bad time. Also, you should probably brush up on linked lists. If you don't know about linked lists, they're used all over the place in operating systems as well. So this declares a 4-character array called buffer, and that's it. So it's 4 bytes long, and it would be at a memory address, and that would be valid for 4 bytes. If you go over that 4-byte limit, you're, playing with invalid memory, and bad things are going to happen, and it's not going to be good. So on Mac OS or Linux, to get information out of a file, there is a function called read. You tell it what file descriptor you want to read from, which represents that open file, so it needs to be the same of whatever we got from open. And then you give it an address where you want to start writing bytes to, and then this argument is how many bytes you want the operating system to write to that array. So in this case, I use size of buffer, which should be 4. It's 4 bytes long. So I tell the operating system you can start at the beginning address, and you can write up to 4 bytes. So it's going to return the number of bytes it actually wrote to that buffer. So that's how many bytes you can successfully read from it that are valid. So I will check for an error. If not, I'll say the read failed. And in here, I have a for loop. Again, you should definitely know how a for loop works. It will iterate over every index that was read, so 0 all the way up to bytes read, which is hopefully it read 4 bytes. So 0, 1, 2, 3, each time through the loop. It extracts a character from that buffer, so first time through the loop it's 0, then 1, then 2, then 3, and then it's going to print it out. So this you might not know. So strings are all ASCII encoded. So what this does is take advantages of the magic numbers in ASCII. So if that byte is any number between 32 and less than 128, it means it can actually print it as a character that you can see and understand, like A, B, C, D, whatever, or whatever. And if it can't print the character, what it's going to do is just print the value of the byte, so in hex. So we can play around with this and dispel some magic, because the ultimate magic is, this is hello world. So this is a fully functioning program that you can execute as a process, and what this process will do is print hello world. And it is only 168 bytes, and it works, which is kind of amazing, but kind of silly how simple it could actually be, because that's actually not that many bytes. For fun, you can go compile hello world in C and see how big that file is, and compare it to this, and tell me if you could ever explain how hello world actually works. I'm guessing the answer is no, and we'll explain this in the next lecture. But first, since we have, I guess, a minute, we can use that read 4 bytes for a bit of fun. And I promise this is not a coincidence. So we can look at read 4 bytes. Uh-oh. So we can actually look at that file, and I will do this quickly. Oh my. So the first 4 bytes of that file are 7F, which is some gibberish, and then the letters ELF, which I swear does not involve me at all. It just happens to be a coincidence. And this is the magic of operating systems. All that means is if the first 4 bytes of that of a file is that, it means it's an executable, and your operating system would try and execute it. So you can run this on any program, your hello world. It's going to look the same, and that's fun. All right, so that's it. See you next lecture.